electron radiate electromagnetic energy even when its speed remains constant? It sounds impossible at first, but this problem reveals a beautiful connection between magnetic force, circular motion, acceleration, and electromagnetic radiation. Let's solve it step by step. An electron enters a uniform magnetic field of magnetic field strength equals to 0.25 Tesla with a velocity of 6 into 10 raised to power 7 meters per second. Perpendicular to the magnetic field. We are neglecting relativistic effects. Our goal is to find the centripetal acceleration and the radiated power. When a charged particle enters a magnetic field perpendicular to its velocity, it experiences the magnetic Lorentz force, which is given by E, the charge on electron, multiplied by velocity of electron, v, and the magnetic field strength, B. This force is perpendicular to the electron's velocity. And a force perpendicular to velocity does something very interesting. It changes the direction of motion without changing the speed. Therefore, the electron follows a circular path. The magnetic force provides the centripetal force. Thus, EVB, the Lorentz force, is equal to mv square over r, which is equal to the centripetal force. Solving this relation will give us a relation for the radius of the orbit of electron, which is equal to mass of electron m multiplied by its velocity v divided by the charge on an electron and the magnetic field strength. Substituting the given values give the radius of the orbit of electron, which is equal to 1.37 into 10 raised to power minus 3 meters or 1.37 millimeters. So the electron moves in a circle with a radius of approximately 1.37 millimeters. Now let's calculate the centripetal acceleration. We know acceleration is given by v square over r, the centripetal acceleration. Substituting the values will give the value of centripetal acceleration as 2.63 into 10 raised to power 18 meters per second square. That's an enormous acceleration. But wait, didn't we say the electron speed is constant? Yes, and this is exactly where the important concept lies. Acceleration is not simply the rate at which speed changes. Acceleration is the rate at which velocity changes. And the velocity has both magnitude and direction. The electron speed remains constant, but its direction changes continuously as it moves around the circle. Therefore, the electron is continuously accelerating. Now the question is that does an accelerating charge radiate? The answer is yes. According to the non-relativistic Larmor formula, power is given by the square of the charge on an electron multiplied by the square of acceleration divided by 6 pi epsilon naught multiplied by the cube of the speed of light. Substituting the values in this particular formula will give us the value of the power radiated by the electron equals to 3.94 into 10 raised to the power minus 17 watts. So the electron continuously radiates electromagnetic energy. Now comes the most important question. How can the electron radiate if its speed never changes? Because constant speed does not mean constant velocity, the electron's velocity vector is continuously changing direction. That means change in direction corresponds to acceleration and therefore it corresponds to electromagnetic radiation. This is the fundamental idea behind radiation from charged particles moving along curved paths. In more advanced physics, this phenomenon becomes especially important in particle accelerators, where rapidly moving electrons can produce synchrotron radiation. So remember, speed tells us how fast something is moving. Velocity tells us how its motion is directed. And sometimes, changing the direction of motion is enough to produce an enormous acceleration, even when the speed never changes. That's the beauty of physics. The most important changes are not always the ones we can see. This was Numerical Challenge 1 from Electrodynamics from Physics Reflections with Saima. Think, question, understand.